Hey everyone, welcome back. So last time we talked about solving a PDE that is the first order and that it is homogeneous. That means that it is equal to 0. Here's another example, but we're going to talk about more about different types of solutions you can arrive to. So first off, here's our PDE. 2 partial derivative of x plus 3 partial derivative of y equals 0. So from earlier, we know that our solution for any type of PDE like this without any actual given conditions, initial or boundary conditions, our solution is going to be the following. Right, we're going to have u of x is any function that is b of x minus ay, where b and a are coefficients. So that means that the solution to this PDE is any function of this form, where u is our function and it's equal to f. It's going to be 3x minus 2y. So that means any function that is being evaluated at 3x minus 2y is our solution. So here's some example of 3 possible solutions. Right, there's an infinite amount of, you can think of a function, then that could be a solution as well. Here you can see this is the square function, and it is being evaluated at 3x minus 2y. Here we have the square root function, 3x minus 2y inside, and here we have a sine function with 3x minus 2y inside. Any of these 3 will work if you plug them into this derivative, part PDE. So let's try that out. Let's say I let my solution equal to the square function. So now I'm saying that u of x equals 3x minus 2y to the power of 2 is a solution to this PDE. Right, so we're going to try that out here. So what we need to do is take the partial derivative of x and the partial derivative of y and then plug them back into this equation, multiply by 2, multiply by 3, and see if we get 0. So let's try that out. So that means we're going to have to find u of x. Use the chain rule. Treat y as a constant. So u of x is going to be 2, right? Chain rule, parentheses, 3x minus 2y times derivative of 3x. So that's going to be times 3. And then u of y, you can simplify this a bit more. So that's going to be 6, parentheses, 3x minus 2y. Take the partial derivative of y. So it's going to be u of y equals, again, chain rule, 2, 3x minus 2y times the derivative of the y variable. 3 goes away because it's just a constant. So negative 2. That simplifies to the following. Negative 4, parentheses, 3x minus 2y. We'll take those two values and plug them back into our equation and see if we get a true statement. So let's see, we have 2, parentheses, u of x is going to be 6, 3x minus 2y. And u of y, right, it's here, plus 3, parentheses, u of y is negative 4. Let's see, negative 4, 3x minus 2y. Is that equal to 0? Well, let's find out. So this is going to be 12, 3x minus 2y minus 12, 3x minus 2y. So it is equal to 0. So that is the solution. So that's from the previous videos. I just wanted to show another example. Now, one thing that you'll figure out once you start messing around with these equations is that any multiple of that function will also be a solution. I know that sounds confusing and it kind of tripped me out, but this is what I mean by that. So we know that this is our solution, 3x minus 2y. But then also anything else can also be a solution, as long as you're factoring out a constant from it. So for example, this can also be a solution. Right? Also, something like this can be a solution. Right? You can verify that. We could verify that right now. So for example, if we take this one here to be our solution and we use the sine function. So let's say we allow u of x, no, let's say our solution is u of xy equals f of, and that'll be what, negative 15x plus 10y. So any function evaluated at that, we'll use the sine function. So we can say u of xy equals sine negative 15x plus 10y. So that will also be a solution. Again, you can take the partial derivatives, and we can verify that in a second. So we're going to work on this, plug them back in, and see if it works. So u of x, you have to use the chain rule for this one as well. So u of x is going to be, let's see, cosine negative 15x plus 10y times negative 15. That simplifies to negative 15 cosine negative 15x plus 10y. Take the partial derivative with respect to y. So that's going to be cosine negative 15x using the chain rule times 10. That's going to give us 10 cosine negative 15x plus 10y. We can plug those into our original equation. So that means we're going to have 2 times u of x being negative 15 cosine. And then we're going to plug in plus 3 times u of y, which is 10 cosine. And is that equal to 0? Well, we distribute, so it's going to give us negative 30. Right, it's going to give us negative 30 cosine. Move this up a bit. Negative 30 cosine negative 15x plus 10y plus 30 cosine negative 15x plus 10y. And sure enough, it does equal 0. So any like scaled version of that will work, right? So as mentioned earlier, if we have our solution equals 3x minus 2y, any other version of that will also work. So let's say I have u of xy equals f of 3x minus 2y. Again, so u of xy equals f of, let's go with 2. So 3x minus 2y will also work. U of xy equals, I don't know, f of 10, 3x minus 2y will also work. And you can simplify this a bit further, so we'll see with f of, let's go with 6x minus 4y. U of xy can be any function of 30x minus 20y. You're kind of curious like why that works. You think about it, where do these numbers actually come from? Right? They come from the original PDE. So if this 4 comes from over here, that would be a negative 4 u of x plus 6 u of y equals 0. You can factor out a 2. Negative 4. So you'll be able to factor out a 2. So let's say this was your solution, right? Then you can say then u of xy equals f of, let's see, that would be a 6x minus 4y. So it's like you can factor it out, right? So that'll be 3x minus 4y. But if you were able to factor out there, you could have actually factored out over here. A 2, I mean, divide by 2, divide by 2, divide by 2. And then you would end up with a Oh, it should have been a 2, my bad. This should have been a 2, and then that could have been a 3. So that's one way to look at it. Another thing that I want to bring up that we are going to see later on is the fact that you can replace a function with the following. So here's something that I might use a little later on, where you can, substitute a function with another function. So let's say you have the function f of 10x plus 5y. You can factor out, obviously, a 5 from this one, so you get f of 5, then parentheses 2x plus y. But you can set this equal to another function. Again, this will be a different function, different name, so function g. And then you can call that just the part that's inside, so 2x plus y. So you can always make the substitution when you can factor out a value, and we'll talk about that a bit later. And that's the reason that also works in this example, where you can take a scaled version of your solution and substitute it. So just quick another example. Let's say you have h, and you have, let's say, negative 5x minus 3. This is the most simplified version of it. So then that would be h parentheses negative 5x plus 3. You can replace this with another function, call that function any other, but it has to be another one. So you can call it, I don't know, let's go back with, I don't know, w, function w, and it would be a function of 5x plus 3. You can set them equal to each other, and we'll talk about in detail more about that. Again, hope that helps. Key thing to remember is that the solution to a PDE is any function of 3x minus 2y, but now we also saw that it can also be like a scaled version of that. Right? All right, hope that helps.